So today, what I will be talking about is actually driven by a simple question, which is carbon, which makes 20% of your body, could that be used as an engineering material, particularly a material that could interface with the human body as a medical device? So what I will do in the next 10 minutes, and in about 30 slides, is establish that story. So again, as a way of introduction, we have a nanofabrication facility in the EIS building, and we have a very large group of about 20 people, undergrads, grads, and PhD students. And we also have a consortium around the lab, which consists of industrial members in San Diego and some other areas. Now, it's also interesting that the handbook that I give to my students, this curiosity, discovery, impact story is an integral part of what we do. So driven by curiosity, discovery, and impact, I work in an area which is an interfacing between carbon and the traditional semiconductor material, which is silicon, and also polymers. So carbon is a very improbable element. In fact, if you look at how carbon came into being, in a dying star, two helium atoms have to get together to form a beryllium. And now, within 10 to the power minus 17 seconds, minus 16 seconds, another helium has to hit the beryllium to create a very unstable carbon, and which 1 out of 2,500 times succeeds by emitting energy. 10 to the power minus 16 seconds, almost could not have existed. But once you have carbon, then you could form oxygen and nitrogen. So it's a very highly improbable element. But what it has done is it has enabled life, because 20% of your body is carbon. Your DNA also contains carbon. It has also been a driver of civilization. For example, art, from Altamira caves in Spain, all the way to the Aztecs, any civilization you mention, they have used carbon. It has also been used in medicine. So with this, people have been experimenting. Can it be used also in engineering? Yes, what happens is our competition is silicon. Silicon is, a nice material. I mean, it's a trillions worth of dollars of economy impact. But in terms of the ability to tailor its property, really there's a huge difference with carbon. With carbon, you have what we call 3 hybridization types, from carbon all the way to graphene. And then you have 0D elements, which are nano powders, all the way to do 3D elements like diamond. All these are carbon. So as an engineer, when I look at this, this gives me what we call a design space. So I could combine all this and make some hybrid materials that could always improve. So for us, the story begins here. So as a background, in the first part, what I would like to talk about is what we have done in terms of using carbon as detection material for neurotransmitters implanted in animal models, and as well as biochemical detection, and what we call multimodal. What is multimodal? We're going to discover. So we make the probes here in San Diego State University in our nanofabrication EIS, and these are some of the stuff that we have built, from energy storage all the way to ECOG, electrocorticography, for example, for a human application. So this has been tested in human patients in Italy and Slovenia, but not published. But we have done animal model probes. Together with the University of Washington, we had a 10-year research program called Engineering Research Center by NSF. So we were able to build these, manufacture this, and then send them to University of Washington, which has access to animal models. So these were the type of devices that we were able to build using carbon. And this is one of a good example of what a carbon looks like. I mean, it's very dark and very glossy kind of structure. Now, with this material, what we have done is, in terms of neurochemistry, we were able to detect dopamine, serotonin, glutamate, and lactate. When it comes to dopamine and serotonin, in vivo, at a record level. My postdoc, now who is a successful professor by her own right, has actually, so we did at 10 nanomolar over here, but she has been able to do at 1 nanomolar, at extremely low concentrations in vivo. So the same material could be used for a variety of material detection of bioanalytes like glucose, uric acid, urea as a wearable device, etc. Now, to give you as an example of what we have done in terms of animal models, one project dealt with as a therapeutic intervention for spinal cord injury. So we had a rat model, a rat model, where actually this was implanted for over 6 weeks, and the sensitivity of the material did not change more than 10%, which is very good, by the way. And then we had another case where we implanted it for about 18 weeks, almost 6 months, where the body did not even encapsulate it, and we were able to get the signal-to-noise ratio, which means the quality of the electrode, not changing more than 10%. So the hypothesis, which is, carbon, compared to metals and silicon, more biocompatible. So that shows already here with 6 months, you have a better signal-to-noise ratio outcome as compared to the traditional ones. So what we have done as an additional, more integrated, what I call multimodal experiment is on a songbird. So together with collaborators at UCSD who have access to songbirds, so what we did was we implanted an electrode in an area called Area X, where there's a dopaminergic circuitry, and their audio, we already have an audio expert here, which is called HVC and NCM. So a PhD student who did her master's in my lab, so she fabricated the electrodes over here, established a very organic collaboration with UCSD, did her PhD, and we implanted this, and what we did was, as the bird was listening, anesthetized, to these songs, we were recording electrophysiology at the top of the cortex, as well as at depth, and also recording dopamine. So electrochemistry together with electrophysiology. So what this allowed us was actually that multimodality. So that's the beauty of carbon. Any of the silicon or metal probes do not allow you to do that. So 2 or 3 publications came out of just this collaboration. So another advantage that carbon has is, by the way, that was taken at SDSU MRI Center a couple of years ago. Carbon electrodes do not also have actually what we call optical artifacts. So if people have an implant, basically a metal implant. In fact, Medtronic, one of the manufacturers of implants, say, in fact, they do have a feature where you have to disable that implant before you go to an MRI. But with carbon, we established both at a low 3T scanner as well as 11.7T scanner that there is no optical artifact as well as heating. So that just proves actually, implantable devices, you could keep it for a longer period of time. Also, it does not interfere with, stuff like MRI. So that was what we have done. So what are we doing now? So encouraged by that, but still not satisfied, particularly there is this thing called conductivity. So carbon is not as conductive as metals, which means you're going to pay a little bit price in energy. So we said, okay, we have to improve this. So to improve that, what we had to do was we had to learn chemistry. The last time I took chemistry was in high school, but I lucked out with my PhD having an undergraduate degree in chemistry, so we were able to understand a couple of things. So the approach that we used was, before even synthesizing anything, the cheapest way to do things is computational. So you build a model. So we have to learn a new discipline called molecular dynamics modeling. So we have different types of polymers. We knew what kind of polymers to use as a precursor for making our carbon. But using models, we wanted to see what happens to these things. If I combine them, would they give me more conductivity, et cetera? So to answer, we built these models. And if the animation works, so I'll run the animation, just only one of them. So in real time, actually, computationally, we could see what happens. So what I'm looking at is so-called 6-member rings. That's called a graphene. That's the wonder material. So I would like to have as much 6-member ring structures as possible, but also I want to have some 3-dimensionality because I need to store charge, etc. So this is one of the polymers, and then this is the second type of polymer. And I'm also watching out with this. Okay, what happens at the end? 1 minute. So we did this, and then also compared our result with what's reported out in our area. Then synthesis. So you've done your modeling. Okay, you've shown that it works, but we have to synthesize that. And for that, we have to do some weird stuff, which is like UV engineering. I did not sign up for this, but some of the polymers that we use, we need to do a fundamental thing. So we did a little of polymer engineering. At the end, we were able to get these new hybrid materials, which indicated to us, so these peaks that you see there, XRD, X-ray diffraction, they told me, okay, now we have a lot of 6-member rings. So that answered our question. So now we're ready to build a newer generation of probes, which are more conductive, in addition to whatever we had before. So if I put everything together, so what we have is a technology, which is state of the art, but you have to look at the opportunities available. So re-engineering carbon, material discovery, and eventually the impact is you have to have what we call a brain-computer interface, or a biochemical sensor, or energy storage. And all this work was done by my students. So we've graduated about 126 master and PhD students from our lab over the past 20 years. And the work is a credit to them more than me. Thank you very much. Questions? Please.
Thank you very much, Sam. I had the opportunity a couple of years ago to tour through your lab and talk to a lot of your students, and the things that are going on there are, first of all, well beyond my ability to understand, but really cool stuff. So I guess the one question I had, and I talked to a few of your students, undergrads, postdocs. What are some of the specific applications have you in your lab been thinking about in terms of how what these implantable carbon devices could do?
So the first one is the most obvious is what we call brain-computer interface. For example, particularly for Parkinson's disease, deep brain stimulation, DBS. So the current system done by a Medtronic actually just goes only one way, which is stimulation, maybe an hour a day, but the problem is there are some side effects because we're stimming right to amygdala, the ancient part of the brain, and the fear factor is gone, and after a year, patients come with problems like gambling and taking risks, etc. So our electrode, what it does is you stimulate, but in the meantime, you measure dopamine. Parkinson's disease pretty much caused by, there may be other complications, but by the death of dopaminergic cells. So by stimming, if you could increase the dopamine and I could measure it, then you could modulate the amount of current that you're putting. So that's the big application that we're striving to get. There are a number of applications related to that, but this, completing the loop, is the application.
Great, thank you.
Absolutely.
So thank you, really very interesting. So you mentioned ECOG, electrocorticography.
Yes.
Which is used in epilepsy.
That's right.
Right,
Yeah.
pharmacoresistant epilepsy.
Exactly.
So because there is this very large, I don't know large, but there are lots of different types of electrodes, and there's a lot of effort that goes into recording from better and better sensors, right?
Right.
So what's the spatial resolution there, and how small are these electrodes that can be implanted? And also, you can have depth electrodes, SEG, not just ECOG, right?
Excellent questions. So the answer to the first one is, for example, we have an ECOG electrode here, a probe, 64 channels. And the dimension, the doctor selected it. He was an Italian doctor, so he told me I could do a 250 micron, which is actually big. We could make these things as small as 10 micron diameter. But with Typical use is about 200 micron for human application. For animal model, for a rat or a mice, you could go as low as 100 micron diameter. But the big, more than that, it's the, particularly for the disease state that you talked about, epilepsy, it's a wider area that's needed. So how many of these electrodes could I pack? So 1,000, 2,000 within that range. So we've shown 64 because that's what they wanted, but the technology in principle could be extended to 2,000 and 5,000 electrodes with 10 to 20 micron diameter. Now, the second part is, could they be made penetrating electrodes? So this guy, the one that we put in the Songbird, is actually a penetrating one. So you can't see them over here, but there are electrodes, 4 electrodes in the shank. So it goes all the way down to the amygdala. So this was a rat model. And we could do the same thing for a human model. So yeah, I don't have the picture over here, but this is again a rat model where we have a shank which goes all the way down. And it also has a surface electrode. So we used sort of origami kind of architecture. So I could measure on top as well as from the same probe, as well as I could go through depth. Looks like I'm the one who's standing between you and you driving home. So.
And you said that they are long-lasting relatively? I mean, how long can they be implanted for?
So the
In the human.
in human, so we don't have the data on human. So I have sent about 15 or 20 of these to a collaborator in Europe. The data is not published, but that was more for acute. So we have a large-scale animal model testing going on right now on sheep with a collaborator. The idea is 6 months. Most of these people, they get tired. We had data on rats for 6 months, and this was again in collaboration with the University of Washington. And the graduate students got tired, and they stopped the project. But after 6 months, then, as I showed you, the signal-to-noise ratio, which is the quality of the electrodes, was really about 90% of what we had already. So we have a 6 months data, and once the big animal model is done, maybe we'll have about 12 months data. Human, larger scale test, no, that's not done. The amount of dollar required for that is something that has to be supported by industry or commercialization. Yes.
Well, and that's kind of where my question was going is, where does most of your funding come from? And then, ARPA-H is doing some really exciting things, and I'm kind of wondering when you think you might be ready for some ARPA-H interactions.
So you asked where does our funding comes from? So the majority of the funding, which actually allowed us to mature this technology, came from what's called Engineering Research Center, NSF funding, which is a 10-year program in San Diego. Actually, in Southern California, San Diego was the only one to have that prestigious funding. So the main partner was the University of Washington, MIT, and we're part of that. So I'm the deputy director still. So it continues, but the funding ended about 2 years. But out of $40 million for the whole center, if my memory serves well, 5 to 6 million came to San Diego State University between me and a number of about 6 to 7 researchers. Now, our current funding is another NSF funding called Broadening Carbon Ring, so that still supports that. We had interest at one point, with the DARPA and ARPA, et cetera, but we're still pursuing that. Right now, part of this is commercialized. We have licensed this technology. The company came out of our lab, so part of this is already licensed. So.
All right. Well,
All right.
if there are no other questions, thank you very much. Thank
Absolutely.
you all of our three speakers. And we have time for folks to talk to our speakers today and hopefully develop some collaboration.